what we're doing at Opus 12 is really developing technology to transform global CO2 emissions from a waste product and a liability into an opportunity. And we're doing that by building reactors or electrolyzers that take just three components, CO2, water, and electricity, and output two different streams, one containing oxygen and another containing our carbon-based fuel or chemical that's made from CO2. So the fuels and chemicals that we're making are exactly the same composition as existing products that today come from conventional fossil resources. So they drop directly into our existing supply chains. Our initial focus is on transforming CO2 into carbon monoxide. And if you're familiar at all with the chemicals industry, you know that carbon monoxide is a really key intermediate in many processes and can be converted into a range of different chemicals, materials, and even fuel. And I guess long term, however, we are interested in directly converting carbon dioxide into a range of different things, and I'll talk about that a little bit as well. So some more details on exactly how our reactor or electrolyzer works. It's essentially the same as a commercial polymer electrolyte membrane water electrolyzer. So water electrolyzers exist at fairly large scale at this point and are used industrially to produce oxygen and hydrogen. And on the far left here, you can see a picture of a commercial water electrolyzer stack where the actual water splitting happens. And in the cartoon just to the right, you can see what's happening in each cell in that stack. So water is fed to the anode catalyst. There it's oxidized to make oxygen, and that releases protons and electrons. The electrons travel through the electrical circuit, and the protons travel through the polymer electrolyte membrane to the cathode, where they combine with each other to make hydrogen in the water electrolyzer. Our device is essentially exactly the same, except we've replaced that cathode catalyst layer with our own formulation that is tuned for CO2 conversion. So it contains different metal nanoparticle catalysts, often supported on carbon, and novel polymer materials that tune the environment to favor CO2 electrolysis. And then obviously we're also inputting CO2 into the reactor now as well. And what's shown here is the production of carbon monoxide, but again, we see ultimately, we think we'll be able to make a whole range of different compounds depending on the identity of the catalyst and the operating conditions used in the reactor. And I think just following up on staff's presentation, this is almost pretty much exactly the same kind of device that he described. It's a zero gap, solid polymer electrolyte type of reactor. One of the reasons that we wanted to use this type of reactor is that it gives us a very clear path to scale up based on existing PEM water electrolyzer scales. So today we're operating in our lab at the first scale here, about a dishwasher sized device that makes kilograms per day of carbon monoxide, and actively working on scaling up to stages 2 and 3. At stage 3, the megawatt scale, this is kind of the largest electrochemical stack size that we envision going to. And that becomes a modular scale where now we can combine as many of those stacks as needed to make facilities of desired size, depending on the amount of CO2 available and the amount of product needed by downstream processes. And I'll talk about a couple of examples of collaborations with customers that I think show how this technology can ultimately be used at very large scale. So last year in February, we unveiled the world's first car part made from CO2. At our lab at Opus 12, we electrolyzed CO2 to make CO, and then used that carbon monoxide as one of the inputs to make polycarbonate. We then worked with Daimler to mold that polycarbonate into an internal pillar cover in one of their cars, and unveiled that in an auto show. So this carbon monoxide is one of the inputs to polycarbonate. It's about 10 to 15% by weight of the final product. And we are actively looking, though, for pathways to make all the parts of polycarbonate more sustainably. And also in this picture, what's highlighted is just all the different materials that go into making a car that could use the direct products of CO2 electrolysis as one of their inputs. So it isn't just polycarbonate that we can make. There's all kinds of different materials that could make this car more sustainably. Another project that was recently announced is a collaboration with Procter & Gamble. We are making an input to their Tide laundry detergent out of carbon dioxide. And so the product that we're making has an over 90% lower carbon footprint than the conventional source of that compound that they would typically use. And I think what this project shows is just the commitment of companies and brands like Procter & Gamble and Tide to make their products more sustainably. We are also working right now on a project to turn our carbon monoxide into fuel through a contract with the US Air Force. And in that project, we're combining our carbon monoxide with hydrogen to make syngas, and then putting that syngas into a Fischer-Tropsch reactor, which will then make jet fuel. We've also looked at alternative pathways to making jet fuel out of carbon monoxide. We've done a feasibility study with LanzaTech. LanzaTech has developed microbes that can actually ferment carbon monoxide instead of typical fermentation processes use sugar, and they can then make ethanol, which can be converted into jet fuel as well. So we demonstrated that our carbon monoxide can be fermented by their microbes in an earlier project. And the renewable fuel that we make through these different pathways has an over 85% lower carbon footprint than conventional jet fuel. So it gives us a pathway to start to decarbonize these really hard to electrify industries like air travel. So those are some examples of where we're at right now with carbon monoxide. But as I said, we are really interested also in moving beyond carbon monoxide to other more reduced compounds. So two products that we're actively working on making right now are ethylene and methane. Methane is a key component in biogas, shown here. And I think one of the challenges in making these more reduced, more complicated products is around the catalyst itself. So size and shape controlled catalyst and alloys look like a really promising route to make these new CO2 electrolysis products. And what's shown here in this picture are actually some cubic catalysts that we've made at Opus 12, but have also been studied in many academic labs. And by controlling the shape of these catalysts, we found what's been shown is that they have much higher selectivity to ethylene and higher energy efficiency. And the hypothesis is that it's really the edges of the cube favor carbon-carbon coupling. And by favoring carbon-carbon coupling, we can select ethylene as a product over methane. Because that carbon-carbon coupling is obviously a key step in making a two-carbon product. This is just one example, I think, of the ways that by controlling the shape, we can control the types of active sites that are present and favor different pathways to make different products. There's also, I think, from many different angles, an advantage to supporting catalysts on carbon. This allows us to get really high electrical conductivity to the catalyst. The carbon is obviously highly conductive, and so it's an electrolyzer. We need to get electrons to the catalyst surface, and so using carbon as a support is a good way to do that. It also helps us stabilize the catalyst particles by supporting on carbon, keeping them from agglomerating together as they might if they were in direct contact. And when we make our catalyst layer out of these supported catalyst particles, We can make it fairly thick, and there's still pores and void space between the carbon particles that allow CO2 to permeate into that layer, so we get good mass transport of our reactant to our catalyst surface. And that porosity stays, I think, is kept stable by having that carbon support there. It also lets us minimize the use of metal catalyst materials while maintaining very high surface areas of the catalyst. And there's increasing evidence that supporting catalysts can also even promote their activity through metal support interactions. And a highlight here, a recent review, I think there's still a lot that's not well understood about how catalysts for CO2 electrolysis interact with the support, but there's definitely many promising examples of where the support can have a beneficial effect. What that leaves us with, though, is a huge space with many, many combinations of catalyst size, shape, composition, and possible carbon supports. And then on top of that, I also want to kind of reiterate what staff said, that the catalyst alone is not enough. We have to find the right environment for that catalyst to work in. And a highlight here, there's many different possible reactor designs for CO2 electrolysis. There's a couple pictured of ones that have been used in industry and in academic labs, and are obviously quite a bit different than our polymer electrolyte membrane electrolyzer being used at Opus 12. And the use of these different reactors and different scales of devices across different labs, it can be really a challenge to try to translate results observed under one condition into other conditions. And even at different scales, right? A small reactor will have very different mass transport than a larger reactor would. And so I think that's one of the issues that we've definitely run into, is that there can be very promising results, but getting that to work in our reactor is not guaranteed. And what we've really found is that for any new catalyst that we want to assess, we need to screen multiple variables at every stage of incorporating that catalyst into our reactor and the operating conditions used in our reactor, in order to make sure that if that catalyst could work well in our system, that we found the right conditions for it to work well. So here I just want to kind of give a really high-level overview of what our catalyst layer fabrication and performance testing look like. So if we have any catalyst or a new catalyst, we would start by mixing that with ionomer binder and dispersing that in a solvent to make catalyst ink. We then take that catalyst ink and put it into one of our deposition systems, where it's laid down on our substrate surface. The solvent evaporates and leaves behind a layer of our catalyst. We then take that the substrate and our catalyst layer, which is now a membrane electrode assembly, which is shown on kind of the bottom right. The black layer is our catalyst layer, and then the plastic looking piece behind it is the polymer electrolyte membrane, and that makes up the membrane electrode assembly. That can then be placed into some of our test hardware attached to one of our test stands, and we can control the flow rate of CO2, of water to the anode, the temperature, and other conditions. And then out of that, we can get performance data in terms of what's our product selectivity and what's our voltage as a function of the current density and other conditions that we might want to explore. Also showing here a little cartoon of what that catalyst layer looks like. So we have in yellow our ionomer binder, and then in black our carbon support, and then in gray the catalyst nanoparticles supported on the carbon. And that it's at those catalyst nanoparticles where the CO2 is being converted to our desired product. So what we've really trying to set up for at Opus 12 is the ability to do rapid iterative testing of new materials for both screening and then, if we do find something interesting, really optimizing the way that material can be used in our system. And there's a lot of variables in our process, and they're all interrelated. So just showing, a few of the major areas, what's the material being used, how are we incorporating that into our device to make our membrane electrode assembly, or MEA? When we assemble that membrane electrode assembly into our cell, what components are we using? And then what conditions are we using to operate that cell? And so I think compared to what some of the speakers have talked about, this is still relatively small scale, but we currently have 3 deposition systems where we can explore different fabrication parameters, and then are ramping up to being able to run 25 over 25 electrolysis cells in parallel to be able to test the cell components and the operating conditions. And then using design of experiments, computational approach to really minimize the number of tests and samples that we need to do to find the optimal conditions for our system. But I think one of the challenges that we're running into then is that for catalyst screening, we need a fairly large amount of material, grams of material, and ideally supported on carbon. And it's not so easy to find sources of some of these really promising catalyst materials at that kind of volume. I think most people here are probably familiar, but the main way that people tend to make these carbon-supported catalysts is fairly straightforward single-step process where you take some metal precursor or salt, mix that with your carbon, and then do some kind of treatment like heat, and you end up with metal nanoparticles decorating your carbon surface. Unfortunately, that gives very little control over the size or shape or really even alloy composition of those particles, but it can be done at a fairly large volume. And so you can get a lot of material out of that type of process in that single step. Making these more kind of shape and size selected particles is often done with multiple steps if we want them to be supported on carbon. So there's some kind of precursor, and in colloidal synthesis, there's some kind of ligand, and then that's put into solution, and there's some kind of reductive process where you end up with these, well-controlled catalyst particles, but it's difficult to do at a very large volume. And then you have to employ a second step to take those particles and support them on carbon, which is also non-trivial. I think what we've seen is that there's lots of, it can be difficult with some of these materials to get really good adhesion between the catalyst and the support, which is really what you want in our type of device. So I think this is a challenge, but also an opportunity and something that we're working on at Opus 12, but also something where we see a lot of opportunities to work with other groups and companies that are also interested in developing these types of technologies. I think one thing we've realized is in developing our CO2 electrolyzer, there's actually multiple innovations that need to happen for that technology to get scaled up and get into the marketplace. And so that's not something that we as a single company, a startup, can do by ourselves. We really need to be part of an innovative ecosystem in order to get our technology, and I think many of the technologies that people are talking about today, out into the world. So yeah, just final thought, I'll leave you with kind of our vision, and I think a shared vision with many here for what the future could look like. And that's really is a world where all aspects of our lives can be lived more sustainably. This is just a picture that's highlighting all of the different materials in this woman's environment that could be made out of the direct outputs of carbon dioxide electrolysis. And there's a lot of opportunities to make our materials, but also, all kinds of different ways that that this person's life could be better. So yeah, with that, just want to thank you for your attention, and I'm happy to take any questions.
Thanks, Kendra, for your nice presentation. And also thanks for joining us so early on your timeline this morning, and same holds for Steph. But again, I think you really added, I would say, an important part to the summit to show the challenges that are still ahead of us in bringing this to a mass market. So people, if you have a question, raise your hand or unmute yourself. In the meantime, I have one question that I'm thinking of myself. So as we already mentioned, that VSP is also moving in the same direction to facilitate rapid experimentation. And same is with synthetic biology. It's an enormous parameter space. It's gigantic. If we test it in the normal process, we will never get to the end. So we need to find the highest speed, the lowest cost of experimentation to really search through this enormous parameter space. What is your view on building such a fully automated foundry, which you see in synthetic biology, is something that companies like Opus 12 and VS Particle could do perfectly. But how is then the relation between those gigantic foundries and all those PhDs, postdocs at the universities that are also trying to contribute to this field? So how should we balance brute force approaches done in these foundries by the knowledge and the capabilities and the infrastructure that all those universities or these academia have? How should we make that into a coherent story that we get collectively to the best outcome in the shortest time?
Yeah, that's a really good question. Yeah, and I'm not sure I have a great answer, but I think it's definitely, as someone who went through a PhD process as well, I think you want the work that you're doing during the PhD to be as relevant as possible to the real world, right? Yeah. Or else what's the point? So yeah, I don't know if there's more opportunities to collaborate with companies, or I think in the United States, there's a lot of opportunities to work through like national laboratories, which really bring together kind of academics at universities plus industrial applications. Yeah. And I think that's been beneficial for us to interact with the research communities through those types of environments as well.
Yeah, at least one of the ideas that we had is we see quite a lot of universities or PhDs, postdocs trying to develop their own high throughput synthesis, but they don't have the right resources. They don't have the capability. You already mentioned that you have 25 microreactors running in parallel to test them. Probably in a few years from now, it will be a couple of hundred if you can scale it effectively. There's no way that a PhD at the university is able to compete to that force. So we should stop them trying to also become interesting and putting time and effort into developing their own high throughput method. That's from my point of view, there's no use. We should keep them focusing on those edges that you can't really investigate with brute force high throughput approach, and really find maybe more fundamental understanding that is a very nice complement to all the high throughput experimentation. Because otherwise, from my point of view, we are just wasting their time by trying to do the same, which is not optimal from a university point of view. Would you agree on that topic?
I think that, something that is different, I think, from being in industry now compared to academia is we don't really have the resources to devote towards like really fundamental mechanistic understanding at Opus 12. But I think that is something that academia, can focus on and really contribute to, and would be really helpful to us. In where do we direct our more brute force approach? Would be really guided by that more mechanistic understanding, but we as a company can't really invest in that because it doesn't directly translate into, you know, the performance of the technology in the marketplace.
Yeah, I can imagine. I see a question coming up from Pau Ferraz.
Yes, thank you. So, Kendra, can I ask you which is the largest size of electrolyzer that you have been able to build, and how long has been in operation for?
Yeah, so we've run electrolysis cells at 700 centimeter squared area, and we're heading up to even larger, kind of over 1,000 centimeters squared. In terms of duration, we haven't run those large cells for very long times because it takes a lot of CO2 and a lot of resources for our team to keep those operational. But at our smaller size cells, so we do kind of fundamental materials testing at 25 centimeters squared, and then 100 centimeters squared is kind of the first demo prototype scale where we'd go to multi-cell stacks. At those scales, we've run things for thousands of hours.
Okay, thank you. And related to one of the things that you mentioned before about like reproducibility, do you think it would be good to try to have some sort of a template 3D printed reactor that you could be sharing throughout different labs and make sure that everybody's using the same conditions? I mean, also making use of the advanced manufacturing processes that we have now in 3D printing.
I mean, yes, I think some kind of standard method for CO2 electrolysis, like catalyst screening, for example, would be really helpful. I don't think we as a company are in a great position to put that out there, but I think that is something that that I know multiple labs are working on. I don't know how helpful it is to have competing ways to do it, but I have definitely heard from different groups that that's something that they are interested in, and that's definitely something we would employ as well if there were some standard approach that everyone else was using. We would want to use that in-house, the same as they were. I don't know about 3D printing, and that's just, I'm not as familiar with how well we could fabricate these types of devices with existing 3D printer technology.
Coming back to the point that you are making is regarding the efficiency of academia. So we speak with many different groups focusing on electrocatalysis, and it's sometimes irritating that we see the same groups or different groups trying to do the same experiments, asking us about the same settings to make a specific type of nanoparticle, and then they will do exactly the same catalytic reaction, maybe a slightly different temperature or a slightly. So from our point, that's a waste from our government's funding to keep people doing the same. So one thing that we are, which is challenging, but one thing that we are at least trying in the coming years is to make an even ground where we know from each other what people are doing. And only by doing that, so effectively using all the resources that we have globally, we have a chance to screen this enormous parameter space in a decent time. But then we really need to make sure that we don't do double work or we don't do the same work. And coming back to the point that I made, I am back. I think we have time for one last question, if there is one. Otherwise, I have one last question. So we with from Synergy, we talked about who should be leading in the different pathways that academia should investigate. I think you are investigating many pathways, from carbon dioxide to carbon monoxide, but also to more complicated molecules. Would you say that you would be better you would be in as Opus 12 better in a position to guide academia compared to, let's say, the big chemical corporates like Shell or ExxonMobil? Or so who should we ask to lead this movement or give guidance to this movement?
Yeah, I mean, I think that there are so many different options. So we've chosen a reactor design, for example, right? But there are a lot of other options out there, and I wouldn't want to limit the entire world to just our type of reactor design, right? There could be some other really promising thing that's out there that we're not exploring. So I think academia is in a good position to explore a really broad space of things and not be limited by, you know, what a company is doing. For instance. So I would say, like, you know, ourselves or Shell or Total or other, you know, companies that are doing work in the space. I think that's valuable information for researchers in this field, but maybe they don't need to limit themselves to just what we're doing, right? And there could be, you know, really exciting stuff that's outside of the scope that any company is looking at.
Maybe that's also an addition to the topic we just discussed, is where should this high throughput brute force approach focus on? Maybe the researchers can be scouting the different routes that then later can be introduced into this high throughput experimentation work, and then you have a nice symbiosis working. After all, I want to thank you for a nice talk. I could talk for hours on this topic, but I think we should give it a stop.